Hello ladies and gentlemen, let's look at electromagnetism tutorial. Now question 1a, explain what's meant by a magnetic field. Let's compare and contrast the different kinds of fields that we have learned so far. Now a gravitational field is where a mass experiences a gravitational force. And an electric field is where a stationary charge experiences an electric force. Now in the same way, a magnetic field is a region of space where a current carrying conductor, a moving charge, or a permanent magnet experiences a magnetic force when placed in the field. Now all three types of objects must be stated in order to get a mark. Okay, so if you need time to copy, you can pause the video to copy the answer. Now let's take a look at part B. Sketch the flux pattern of the magnetic field with the following. Now, the important thing to note here is that all magnetic fields are loops with no beginning and no end. Now, so for a bar magnet, you have to draw at least one loop, or if not two loops. The magnetic flux travels inside the bar magnet from south to north, but this part of the flux is normally not drawn in the diagram due to clarity reasons. Okay, so normally we don't draw this. For the circular coil carrying a current, make sure to also draw the loops outside the coil. A magnetic flux travels in a loop with no beginning and no end, very unlike electric field, which begins at the positive charge and ends at negative charge. Now along a solenoid, let's take a look at how the current flows in the solenoid. Using the right hand grip rule, we see that in order for the current to flow like this, the north pole of the magnetic field must be pointing in this direction. Now once again, for the solenoid, try to draw at least one loop around the solenoid to show the examiner that you know that magnetic fields go around in loops. In the middle of the solenoid, there is a uniform field inside here. So with a uniform field, we have a regular spacing of field lines. So once again, the magnetic flux inside the solenoid flows from south to north, but outside the solenoid, it flows from north to south. Okay. Now for a long straight conductor, top view, the right hand grip rule is once again used to determine the direction of the magnetic flux. Now please note that you must draw at least 3 circles which are concentric, and the spacing increases with distance from the wire. So it's a good idea to bring along a compass set in order to draw these diagrams. Okay. Now let's move on to question 2. 3 separate coils of insulated wire are connected to cells as shown. They are placed partially overlapping. Now in order to find out how the magnetic fields move around the coils, let's use 3 different color pen. Now for coil that's on this side, alright, using our right hand grip rule, we can tell that the magnetic field in region 1, 4 and 5 is going into the page. So for this coil, the magnetic field goes into the page in the center of the coil, and then outside the coil it comes out of the page. So this means that in regions 1, 4 and 5, the magnetic field is going into the page, but outside it's coming out of the page, outside the loop. Okay, now we're going to do the same for loop number 3, but this time in blue color. So let's take a look at the blue color circuit's current. Now using a right hand grip rule, we know that inside the loop the field is going into the page, but outside the loop the field is going out of the page. Alright, so that's for region 4, the lower loop. Now for the loop on the right, we're going to use red color. Okay, so let's take a look at how the current moves around the loop. Now based on this, inside the loop the field is coming out of the page, but outside the loop the field is going into the page. Alright, now we're going to erase all the unnecessary crosses and dots so that we can see the magnetic field more clearly. and we'll also erase the wires currents as well, current directions, so that we can see the magnetic field more clearly. Now, take a look at region 1. In region 1, there are 2 crosses and 1 dot. That means that the magnetic flux lines are not acting in the same direction. Region 2 also not acting in the same direction. Region 4 also not acting. Now, region 2, they are acting in the same direction. And also region 5, they are also acting in the same direction. So the only regions listed which are the magnetic flux is acting in the same direction is 2 and 5, and that's what's meant by reinforce each other, means that the flux is in the same direction. Okay, so that is question 2. Now let's take a look at question 3. 2 vertical parallel conductors are 0.12 meters apart and carry currents of 2 amps and 4 amps. Determine the distance of a point where the magnetic fields neutralize each other. Now, so we'll draw these 2 currents going into the page, right? One of them is 2 amps and one of them is 4 amps, and the distance apart is 0.12 meters. Now, if we draw the magnetic field inside around the wire, okay, we'll use our right hand grip rule to see that the magnetic field is going clockwise around the wire. Now, this means that somewhere in the middle, this magnetic field from X is going to be in the opposite direction as the magnetic field from Y. Now, based on what we know about the strength of the magnetic field, this must be closer to the 2 amp and it must be further from the 4 amp in order for it to be a neutral point. Alright, so let's label this distance X, and this distance will be 0.12 minus X. So at the neutral point when Bx is equals to By, we have mu naught over 2 pi, the current of X, which is 2, divided by the distance, will be equals to mu naught over 2 pi, the current of Y, divided by the distance 0.12 minus X. Now, cancelling the terms and solving using a graphic calculator, we get X is 0.04 meters or 0.040 meters to 2 SF. So this is how to solve a neutral point question for wires. Now, let's take a look for part B. What's the magnetic flux pattern between X and Y? We know that the neutral point is somewhere here, which means that there is no field inside here. So using our right hand grip rule, we know that the field goes around in a circle like that, and the field goes around in a circle like that. What about outside? Now outside the field, it will go around in a circle, but as it comes in, because there's no field, it will be bounced back out again. And it's no field, so it's bounced back out again. So, okay, so that's one way to draw it. Right, so then we can draw the field in this direction. Now, of course, we have to try to make the field smaller around X and larger around Y, since Y has a larger current and X has a smaller current. So because Y has a larger current, it also has more rings around it, so you can feel free to add more rings. Notice that the spacing of the rings increases as the wires go up. Okay, so the spacing increases. This is how you would draw the flux pattern. So it looks like Among Us. All right. So that's how we try to remember it. Okay. Next, a conductor carrying a current I with length L is directed into the paper as shown. What is the magnitude and direction of the force experienced by the conductor? Now, if you draw your Fleming's left hand rule, okay, this is what your hand will look like. Your thumb will be pointed in this direction. Your pointer finger will be in this direction, and then your middle finger will be in this direction. Alright, so this will be what your hand looks like. Okay, so inside here, the B field is pointing into the page. Over here, the current is pointing to the top and right. And so, your force will be pointing to the top left. So this is where your force direction will lie. which is around the region of 300 degrees bearing. So A and C are out. Now the question is, how much is the force? Now the magnetic flux is traveling, the magnetic flux linkage, the flux lines is traveling into the paper, and then the current is going to the right. So the angle between the flux to the current is 90 degrees, is perpendicular. This means that the force will be BIL sine 90 degrees, meaning that maximum force will be achieved. So the answer is B. Okay, so this 30 degrees is purely a distraction, and it does not affect the force at all. So do not put the sine 30 degrees inside here. It's purely a distraction. Okay, now let's look at question number 5. For question number 5, two magnets rest on the top pen balance. The reading on the balance is 100 grams when no current flows. When there is a current of 2 amps, then the reading changes to 102.6. Basically, the reading increased. So what happens is that when the current flows, it exerts a force on the magnet downwards. Okay, so we can argue it like this. Since there is a current in a magnetic field, there will be a force on the wire upwards due to the magnet. So this is the force the magnet push the wire. Right, so therefore the wires will push the magnet down an equal and opposite force. Force of the wire pushing the magnet downwards. Okay, because of Newton's third law. So there's an increase in the reading because the current is flowing in the magnetic field, and then the magnet pushes the wire upwards. So by Newton's third law, the wire pushes the magnet downwards. Okay, a current flows through a wire, therefore a magnetic force is exerted on the wire. So the magnetic force of equal and opposite direction is exerted on the magnet downwards, increasing the balance reading. Now let's take a look at how to work out the reading on the balance when the current of 3 amps flows in the direction YX. Now, first of all, let's use some logic. When the current flows from X to Y, the reading increases by 2.6 grams. So when the current flows from Y to X, the reading should decrease, instead below 100 grams, isn't it? So when you move the current in one direction, it pushes the magnets down and it increases the readings from 100 grams to increase it to 102.6 grams. So when the current flows from Y to X, the reading should decrease. Now let's use a bit more logic, okay? When the current is 2 amps, the increase in the reading is 2.6 grams. So when the current is 3 amps, the reading should change by more than 2.6 grams. Okay, so now let us examine exactly how the reading will change. Now the force exerted by the magnet will be equals to BIL. This means that the force of the magnet is proportional to the current I. Okay, if the current increases, the force also increases. Now, so we can use a ratio theory to look at this question. Now, when I is 2 amps, the force is equivalent to a reading of 2.6 grams. So therefore, when I is 3 amps, the force is equivalent, okay, to 2.6 grams times 1.5, isn't it? That would be 3.9 grams. Okay, therefore, the reading will be 100 minus 3.9 grams, which will be 96.1 grams. So this is the final answer. Okay, 96.1 grams. Now please note that the answer given in the answer tutorial answers is incorrect. The reading should be 96.1 grams, not 96.7 grams. Okay, right, so this is the answer for part 1C.